Alright, this is a brief further explanation of redox chemistry. Hopefully you've already seen that one introduction video by Tyler DeWitt. Wanted to explain a few other things here. First, you should remember redox stands for reduction, oxidation. So reduction and oxidation are opposites. You can't have one without the other. You can't have a reduction without an oxidation. If you remember, reduction is the gain of electrons. Reduction is a loss of electrons. And if something is going to lose electrons, they don't just poof into non-existence. They have to go somewhere, and wherever they go is gaining them, and that substance has been reduced. So that's where we get this oil rig business. Oxidation is loss of electrons, reduction is gain of electrons, or the one I prefer is Leo the Lion says grr. Loss of electrons, oxidation, gain of electrons, reduction. So we could describe reduction and oxidation just in terms of electrons, and that works all the time, but the term oxidation implies oxygen. So we can also describe reduction and oxidation in terms of oxygen. Oxidation is a gain of oxygen. What I mean by the gain of oxygen is that we are gaining bonds to the element oxygen, or bonds to atoms of oxygen. Reduction, then, being the opposite, would be a loss of oxygen. So, since oxidation, the quintessential oxidizing agent, or the thing that does oxidizing, is elemental oxygen, we have this term oxidation. But it turns out that we can also describe redox chemistry with in regard to hydrogen. So in this case, hydrogen and oxygen tend to be opposites. Right? So whereas reduction is a loss of oxygen, it can also be thought of as a gain of hydrogen. And whereas oxidation is a gain of oxygen, it is a loss of hydrogen, or a loss of bonds to hydrogen atoms. I'll show you some examples of this in a chemical reaction in just a moment. In Tyler's video, he briefly talked about oxidation states, and in the other video in Crash Course Chemistry, they go into a little bit more detail on oxidation states. And so let me just write that down as well. Because electrons are negatively charged, right? We're gaining electrons, which is a negative charge. Reduction is a decrease or a decrease in the oxidation number. And if you're not sure what an oxidation number is, go back and look at those videos, or stay tuned, I'll explain it here as well. So because reduction and oxidation are opposites, if reduction is a decrease in the oxidation number, that's where we get the reduction from. Oxidation is an increase in the oxidation number. Because we're losing electrons, we're losing a negative charge, the oxidation number actually goes up. You can think of it as like in your finances, if you discharge a debt, in other words, you pay off a debt, your net worth has gone up because you've lost something that's negative. You've lost that debt. So oxidation number increases. Okay. So make sure you have these definitions straight. these two definitions with the loss of oxygen, gain of hydrogen, gain of oxygen, loss of hydrogen, they do not always work. But when you see them, it makes it a lot easier. Now, you can always assign oxidation numbers and see if the oxidation number is either decreased or increased. That correlates to either the gain or loss of electrons. But we're not going to go into that much detail. These definitions of losing oxygen, gaining oxygen, this is primarily what we use in organic chemistry. So let me just write here, organic chemistry. We talked a little bit about organic compounds. And if you take biochemistry, you'll be focusing on these two definitions as well. So let me just talk a little bit more about oxidation numbers. Tyler didn't talk too much about it, and in the crash course chemistry they went into a little bit too much detail. There are rules for assigning oxidation numbers. I'm going to abbreviate oxidation numbers ON. Alright, so rules for assigning oxidation numbers. You don't need to know all these rules, but there's a couple that really make it helpful. The first one is all free, uncombined elements have an oxidation number of 0. And so in Crash Course Chemistry they did talk about this. What this means is if you see an element such as elemental oxygen, or elemental hydrogen, or elemental chlorine, their oxidation numbers are 0. So I'll put here zeros. These all have an oxidation number of 0. The trick here is to remember that even though this is an oxygen molecule, it is still elemental oxygen. It is not combined with any other element, so it is not a compound. And its oxidation number, or its oxidation state, is 0. Other elements, if you have like elemental iron, or we'll see in a reaction in a moment with elemental zinc, they too will have an oxidation number of 0. We'll come back to this in a little bit. The second one, also discussed in Crash Course Chemistry, is for ions. The oxidation number is the charge of the ion. And this goes for ions written, say, if we had something like sodium ion plus, I don't know, the chloride ion, giving us sodium chloride. The oxidation number here, we've actually listed it as an ion, so it's +1. Here it's -1. But even in an ionic compound, such as sodium chloride, we know that the charge here is +1 for sodium and -1 for chlorine. Okay, and that's about as far as we need to go for assigning oxidation numbers. You can look at the explanation in the Crash Course Chemistry. It goes into much more detail, but this is enough for us. Alright, the main thing that I want you to recognize is number 1. Because what I'd like you to be able to do is identify reactions that are redox. So we'll go back and review these reactions that we talked about. We had, I think, 5 different types of reactions. We had, let's see, we had double displacement. We had single displacement. We had combustion. And then we had those two that were opposites of each other, combination and decomposition. Now this is not the same order that I gave it to you before, but there's a reason for that. If you care to memorize things, you can memorize that double displacement is never a redox reaction. If you recognize a reaction as being double displacement, it is not redox. Conversely, if you recognize a reaction as single displacement, it is always redox. And if you recognize a reaction as a combustion reaction, remember combustion always gives us the products of CO2 and water, this is also always redox. So double displacement never, single displacement and combustion always redox. These two guys, combination and decomposition, may or may not be redox. So that's a trickier situation, and then you have to go back and look at these other definitions to find out, is something gaining electrons, is oxidation number increasing or decreasing, and that sort of thing. Alright, now well, let's look at a combustion reaction first. Combustion of methane, natural gas, with oxygen in the atmosphere. Right, combustion always gives us carbon dioxide and water. I won't go through all the steps methodically, but this is not balanced. We should balance it. There are 4 hydrogens here, only 2 here, so I'm going to put a coefficient of 2 there. This gives me 2 plus 2 waters, so oxygens, 2 oxygens here, plus 2 more, that's a total of 4. There's only 2 here, so I need a 2 here, and now it's balanced. Okay. This is a redox reaction, it's combustion. One way you can tell it's a combustion reaction, or one way you can tell it is a redox reaction, is it has a free uncombined element. Any reaction that has a free uncombined element, including the 7 diatomics, so I'll just make a little note here. Remember the 7 diatomic elements. Oxygen being one of the 7 diatomic elements. If it has a free uncombined element like that, remember our first rule for assigning oxidation numbers? All free uncombined elements have an oxidation number of 0. Well, if it is 0 and it's going to react, it's going to change from something that is not O2, or to something that is not O2. From oxygen with the oxidation state of 0 to something that is not oxygen, or otherwise it wouldn't be a chemical reaction, right? It has to change. That means the oxidation number must also change, and if the oxidation number is changing, it either has to decrease or increase. So if it increases, it's been oxidized. If it decreases, it's been reduced. So here, oxidation number, or oxidation state is 0. Water, or not water, oxygen, if it's in a compound, now right now it's O2, but it's CO2. It's not elemental oxygen, it's in a compound, carbon dioxide. So in a compound, oxygen is almost always -2, unless it's in a peroxide or superoxide, but you probably won't see those. So oxygen, if it goes from 0 to -2, it's been reduced. Right? The oxidation number went down. Right? So a decrease in the oxidation number, that's reduction. It gained electrons, and it gained hydrogen. So we can use that definition here. oxygen here is gaining hydrogen. It goes from just plain old oxygen, two oxygen atoms bonded to each other, to now an oxygen-hydrogen bond. So it's been reduced. Oxidation number went down from 0 to -2, and it gained hydrogen. Now remember, oxidation and reduction are opposites, which means they always must come in together, come in pairs, right? You can't have an up without a down, a left without a right, an on without an off, or an oxidation without a reduction. And so if oxygen is being reduced, what is being oxidized? Well, here we see carbon. I won't assign oxidation numbers here because it's not necessary. Oops, we don't need that. Carbon is combined with 4 hydrogens. Here is combined with oxygen. So it gained oxygen. The carbon did. It also lost hydrogen. So gaining oxygen, that's an oxidation. Loss of hydrogen, that's an oxidation. Another reaction, this is something that Tyler DeWitt did, and I'm going to write this a little bit differently. We know Tyler used just plain chlorine as what we would call a radical. Chlorine is in group 7, it has 7 valence electrons, and he just used a single chlorine atom. But we know chlorine does not exist as a single atom like this. Instead, elemental chlorine is one of the 7 diatomic elements, so it's not like that. It's Cl2. So if sodium is going to react with chlorine, it's going to react with something like this. And so what happens then, if you, well, let's finish this reaction. We get the sodium ion and the chloride ion, but there's 2 chlorines here, right? So we'll use a coefficient of 2. And to balance this, we know, actually we can go this way as well, we know we're going to get 2 sodium chlorides, so we need a 2 in front here as well. So 2 sodiums plus elemental chlorine plus elemental chlorine, Cl2, gives us 2 sodium chlorides. And so what's actually happening here is this bond is breaking, and for reasons I won't get into, when you only move 1 electron, you use a half-headed arrow. I'm going to put this 1 electron over on this side, and this 1 electron over here on the right. And so 1 sodium will donate its electron to 1 chlorine, and another sodium, right, there's 2 sodiums, will donate another electron to its chlorine. And that's more appropriately how you get 2 sodium chlorides, or if you wish, I forgot the 2 here, we need a 2 here as well. We get 2 sodiums, each with a plus charge, and 2 chlorines now, they have each gained an electron, so it's -1. Gained an electron, -1 charge. So I just want you to be aware that chlorine does not exist like this. More appropriately, it should have been Cl2. He also talked briefly about half reactions. And so let me just write this half reaction here. I'll just do this briefly. Sodium goes to sodium ion, and it lost an electron, if you recall. And then the chlorine, elemental chlorine, put an electron here, has 7 valence electrons. It gains an electron and becomes the chloride ion, right, with a -1 charge. Okay, these are half reactions. Now, I'm not going to say anything more about half reactions, but the reason I'm going into this is because if you think about what's going on here, electrons are being transferred. If we have a way of isolating the two half reactions, so we have, this is the oxidation half reaction, this is the reduction half reaction. So I'll put the oxidation reaction here, doesn't matter what it is. I'll put the reduction reaction over here. If we have a way of isolating these two, but we still need to connect them so the electrons can flow through, whoops, the electrons, yeah, the electrons are going to go from the oxidation to the reduction, right? The electrons are going this way. If we have a way of isolating these two half reactions, we can connect them, I don't know, with something that conducts electricity like a wire, and then we can put, you know, like a little light bulb, and drive these electrons through the spontaneous transfer of electrons from the oxidation to the reduction. We can create electricity, and that's exactly what a battery does. So the reaction that's occurring in your typical 1.5 volt alkaline dry cell, there's a copper top or a Energizer bunny or whatever, is this reaction. So what we've done is we've isolated the two half reactions. The whole reaction is this. We have zinc plus this manganese dioxide goes to zinc oxide, and this Mn2O3. Alright, so what's happening here? Zinc is getting oxidized. How do you know? Well, first off, how do you know it's a redox reaction? We have elemental zinc. It's a free uncombined element. Any reaction has a free uncombined element must be redox. So zinc is gaining oxygen. It's been oxidized. So that's oxidation. Oxidation. This one is a little bit trickier for the manganese. Manganese here, we have one manganese atom combined with two oxygens. Over here we have one manganese combined with three oxygens. So the ratio here of manganese to oxygen is 1 to 2. Here, and how did I get that? Well, one manganese, two oxygens. Here it's manganese to oxygen, it's 2 to 3. Okay, or 3 oxygens for every 2 manganese. Put it this way: 3 oxygens for every 2 manganese. 3 over 2 is 1.5, isn't it? Here the ratio of oxygen to manganese, well, 2 to 1, or I should say 2 over 1, 2 to 1. Okay, so manganese is actually getting reduced. It's going from 2 oxygens per manganese to 1.5 oxygens per manganese. So a little bit trickier, but again, if there's an oxidation, there must be a reduction. So this is the reduction, and in fact it is losing oxygens if you do the calculation this way. The other way to do this would be to assign oxidation numbers. I'm not going to bother with that. I just want to impress upon you the fact that something called electrochemistry and all electrochemistry or all electrical power generation involves redox reactions and this electrochemistry. Now here it's a battery, but even if it's the coal-fired power plant down in Oak Creek, they're burning coal, which is essentially graphite, a form of carbon. They're burning it, combining with oxygen in the atmosphere and producing carbon dioxide. That's also, of course, a redox reaction. Okay, Let's go back here and look at the single displacement. We already did combustion. I said it's always redox. Let's look at single displacement and then combination and decomposition briefly. Single displacement, if you recall, one element displaces another element. So now A is dancing with C and B is all by his lonesome. So an example of this would be zinc, let's say copper sulfate. The zinc displaces the copper. We get zinc sulfate and elemental copper. The reason I can say single displacement is always redox is because we have a free uncombined element in the reactants and a free uncombined element in the products. So A and B here. Free uncombined element. Anytime you see that in a reaction, you know it is a redox reaction. For combination and decomposition, we can have a combination reaction like I just showed you, although I didn't call it that. Right? Sodium and chlorine come together to give us sodium chloride. This is redox. How do you know? There's a free uncombined element, actually two, both sodium and chlorine, free uncombined elements. But it doesn't have to be. You could have water and carbon dioxide. They combine to give you carbonic acid. Just because you don't see a free uncombined element in the reaction doesn't mean it's not redox. You really need to assign oxidation numbers to know if it's redox or not. But for a simple one like this, I'm not going to ask you if it's redox or not. But this one is not redox. And we can go through and assign oxidation numbers. In a compound, hydrogen is always +1. Oxygen, as we said before, is almost always -2. So oxygen and carbon dioxide, -2. Oxygen here, -2. Hydrogen, always +1. Well, almost always. If it's combined with a metal and a hydride, it could be -1, but for us it's almost always +1. Carbon is a tricky one. Carbon can have variable oxidation numbers, but one of the rules that they went through in the crash course in chemistry is that the oxidation numbers must add up to 0 or add up to the charge on the particle. This carbon dioxide is a neutral covalent compound, and if there's two oxygens, each with a -2, then carbon must here must be +4, right? So we have a +4 from the carbon and two oxygens, each with a -2, right? So this whole charge balance business also applies to covalent compounds, but to their oxidation numbers. These are not ions. Similarly here, we have two hydrogens, each with a +1. We have three oxygens, each with a -2. -2, -2, -2, that is a -6. Two hydrogens here, that's a +2. So what's the carbon? The carbon has to balance this. We have to have a total of +6 to balance the -6. So carbon naturally has to be +4. And if you look at these oxidation numbers, then none of them have changed, and so it is non-redox. Again, I'm not going to ask you to do that. This is just more of a way of explaining the usefulness of applying oxidation numbers to figure out if something is redox. For you, what you need to remember is double displacement reactions, never redox. Single displacement, always redox. Combustion, always redox. There'll be some reactions where it might be kind of tricky to see if it's redox or not, and I'll ask you to focus on these two definitions regarding oxygen and hydrogen. Gain of oxygen, gain of hydrogen, and so forth.